So thanks for the kind introduction. Let's get into the meat of the topic. We want to talk about digital twins and how AI can be done on digital twins to really solve the problem of resiliency in supply chains, which is a very hot topic right now, as you know. And we want to stage this conversation in like three parts. The first part is to talk a little bit about the inherent challenges of complexity that you see in modern supply chains. So I'll talk a little bit about that. Then I'll talk a little bit about what is the right model and paradigm for this new state of affairs. And of course, I'm going to make the case that digital twins are that new paradigm. And then I'll hand it over to Mayank to talk about some really interesting AI applications that you can build on top of digital twins, how they are kind of like made for each other in a sense. Let's first kind of agree, all of us together, that supply chains are a very complex beast, especially modern supply chains. And they are complex in multiple ways, and that's where it gets very interesting. So first of all, supply chains are complex because they are in a big complex network of flows. And the things that flow over this network, they of course are things like parts, raw materials, things like that. You also have services, electricity, bandwidth, water, human resources also flowing along the edges. But then there are also abstractions, and they're important abstractions that also flow along the edges, things like risk, value, trust, liability. These are very important things in supply chain. And so those are also flowing through the network. And so you have to really think of this as a complex network of flows. That's one kind of complexity. Secondly, supply chains are very complex dynamical state machines. And this is like the more classical view of thinking of supply chains, right? So why is it dynamical? Because all the nodes in the supply chain, they themselves have memory. They are small state machines, but then they are all feeding each other, as you can see on the right-hand side here. So that makes it into one big, huge state machine. And the big global state is the combination of the substates of all the nodes. And, the truth of the matter is that this huge state machine is only partially observable and partially controllable. And, in many cases, it's not even stable. We would like it to be stable, but the last few years have shown very clearly that these supply chain dynamical machines are not stable. And then the last part of the puzzle is really that supply chains, and this is a modern part of the conversation, right? A modern view of supply chains, that they are also games, they are multiplayer games. And why are they a game? The reason is that all the different stakeholders who kind of control all these different nodes in the supply chain, they're not all under one roof, or they're not controlled by one corporate entity. So they're not all driving towards the same KPI or the same business objective. They're all independent businesses. Often there are even regulators involved, governments involved, and things like that. And so when you're looking at this kind of situation where everybody has their own KPI that they're trying to optimize, they have their own business objectives, and they're kind of playing with each other, but they're not necessarily all trying to score goals in the same direction, then you get a proper multiplayer game. Now, just because it's a game doesn't mean it immediately is a hyper-competitive or malicious game, right? You can actually have games that are fully cooperative. In game 3, that's well known. But nevertheless, being a game, you have like the basic paradox called the prisoner's dilemma, that through cooperation, actually everybody could get better, but who takes the first step? And that is further exacerbated by the problem that there is limited visibility into each other's actions and goals and things like that. So all these things kind of make this game very interesting, from a theoretical perspective, but also it makes an urgent problem to address. So the second point I want to make is that being complex means that there's like a Jekyll and Hyde property of complex systems. If complex systems are designed poorly and they have poor incentive structure, it can lead to a whole bunch of trouble, right? They are very sensitive to perturbations. They can have these disruption cascades, like a domino effect. One thing fails here and like all the things down the chain can fail. And it's not even a chain, right? It's a network. And you can actually get honest to God chaotic behavior as defined in theory, regimes of chaos, right? And then also because it's a game, there can be, non-cooperative behavior or even outright malicious behavior, which can be like almost like a security problem, right? So all these problems can occur in complex systems. But however, there's a Dr. Jekyll, I guess, right? The good person of that duo, the good persona. So there's a Dr. Jekyll part of that also, right? Which is like that complex system can also be a lot of power, a very powerful and a force for good, because they can self-organize, they can self-heal, they can have built-in redundancy, they can actually enable cooperation and co-optimization. But to do that, you need to design them well, and you need to incentivize the different players in the right way. So that's the stage of this conversation, right? So With that in mind, now I want to make the second point that in order to do a good design of complex systems, we need to actually have a good and strong modeling framework. That is the missing problem right now. It's not like people are not willing to cooperate or they're not willing to optimize. This is not a problem. The problem is that they don't know where to start. They don't know how to even represent this reality so that you can actually meaningfully deal with it, right? And like every model should be simple in the sense it cannot be as complex as the reality itself. Otherwise, it's useless. But it should not be simplistic. So there has to be like this very well calibrated representation with some fidelity. But the fidelity doesn't have to be perfect fidelity, because otherwise, you'll have too much complexity in the model itself. So that's number one. And then it needs to enable a trifecta of capabilities, right? It should have a good language for representing and querying language, querying the knowledge that is embedded into the model. And it should also have some great visualization tools. That's a very important property of good models, because without visualization, because we are very visual creatures, we like to see things spatially. Humans are singularly bad at understanding time series, but they're very good at understanding spatial layouts of things, right? So visualization becomes very important. And then we also want this modeling framework not just to be a passive read-only model, but actually it can be something that you can activate. It should have surfaces and affordances and buttons, which can be completed through AI and through automation, where you can make things happen. That model will actually cause things happen in the real world. So it kind of closes the loop. And if you get this right, then you can actually test ideas and plans before you implement them. And you can do this holy kind of holy grail of supply chain modeling, which is, can we test out for contingencies and build resilience to disruptions before they happen? And the goal problem here is that disruptions are by nature not very predictable. Right? You cannot predict a hurricane well, not with that great accuracy. So you can certainly not predict things like an earthquake or a revolution or an outbreak of a disease. But you can definitely predict what will happen in case that hypothetical scenario is true. And so here the word prediction has to be used in that sense that, we cannot test out some extreme conditions, which we don't know when they will happen, but we are pretty sure they will happen at some point or time. And we see how our system is going to perform. So now I'm going to switch gear and talk about digital twins. So digital twins are, in my opinion, the new paradigm of modeling. This is that is going to be used extensively in supply chains. And this was inspired by Internet of Things primarily. But it's much more than the IoT case, definitely, when we go to supply chains, because we are not just representing physical things like assets, machines, trucks, and so on, warehouses, but we are also representing abstractions. We can represent a hurricane in the supply chain digital twin. You can represent products, you can represent customers, you can represent processes, and so on. Gartner has this very kind of specific and nicely calibrated definition of what a digital twin is. But I just want to make the point that digital twins are getting a lot of mindshare and coverage right now in the industry. And in many ways, they are going to be the language through which this problem of resilience is going to get solved over the next few coming years. So a digital twin actually has four, in my opinion, there are four aspects to it, right? The first aspect is how is data represented in it. So it's like data ingestion, bringing the data and staging it semantically. That's one part. That data can come from systems of record. It can come from like logistics, inventory, demand, production, and all those processes. It can also come from telemetry, IoT, as we talked about. There is another kind of data that comes in, which is like sensing data that comes from like the outside world, where you can sense what's happening in terms of demand and supply, risks, financial signals by looking at web search, by looking at social signals and things like that. And then there is this clear third alternative, which is shared data. Your business partners can actually agree to share their process data with you, provided there's like a quid pro quo and you share data with them. And so shared data is like another big surface from where you get data into the digital twin. Once you have the data in, then AI kicks in, right? And there are two basically flavors of AI. There's predictive AI, which basically says that if this is the state of your supply chain right now, here are the things that are likely to happen. And you basically provide a likelihood, and you provide some human understandable reasoning of why you think that is going to happen. So that's the predictive part. And you can predict risks to demand, supply, you can do alerting on it. But an even more interesting kind of AI use is actually prescription, where you say, not just that this is likely to happen, but if you want to change that outcome, here is the set of things you need to do. So if something bad is about to happen, then you can actually prescribe. If you want to avoid that bad outcome, here are a set of things you can do to actually mitigate that badness. Or conversely, if some good kind of thing is already happening, you can exacerbate it. You can actually make it better, drive it up, that KPI, by taking some other actions. And so prescription is kind of like starting to bleed into notion of planning and multi-action and inventory optimization, those kind of things. the main thing I want to call out is that traditionally this was viewed as very much an operational research kind of area. And now definitely AI is very strongly embedded in it. And the reason is that, objectives and constraints that are part of the planning framework, they are nowadays often AI driven. So for example, in one of the constraints in your plan will be like plan my inventory allocation, but with the requirement that the risk of stock out in the store should be less than 2%. How do you calculate that risk? That risk actually comes from an AI model. So the AI model is inside the inner loop of the planner as it's trying out various configurations. So it's indeed like a really great marriage between OR and AI, the modern way of doing it. And then, of course, when you have that AI and you have those prescriptions, then you can do what-if analysis. As I said, you can basically assess what will happen if some kind of mutation happens to the supply chain. And those mutations can be driven by us in the sense we plan that we will make this change. We'll plan to open a new warehouse or introduce a new product or whatever. Or the mutations can happen from nature. Nature just throws a disruption at you. A hurricane happens or a war happens, like what's happening right now. And so in all these cases, you want to kind of do that hypothetical analysis a priori and say that what if this happens? What will be the effect on my KPIs? What will happen to the likelihoods of various events and so on and so forth? And that leads to this kind of broad topic of network optimization to drive various KPIs like efficiency, agility. Sustainability is a very big important KPI now that everybody is focused on. And then collaboration and automation are the two ways in which you close the loop. You heard the previous speaker talk a lot about the human in the loop. That is actually one of the first ways of closing the action loop, right? Where you show a risk to a set of humans who are like experts there, and then they'll assess it and look at it, and they go and basically press the red button in the real world, say that we need to take this action to prevent this risk from blowing up, right? And then, of course, over time, as you learn from the humans' action, the humans can start saying that, hey, I do this repetitively all the time. Can we now make this into a workflow that can be automated automatically whenever this state happens or this prediction happens? And the humans can still be informed, but they don't need to always press the button themselves. So that will be like a collaboration to automation. That transition can be done gracefully with humans more and more doing the work of supervision rather than actually taking actions. So I do want to hand it over to Mayank soon. So I just want to give you a couple of quick examples of how a digital twin looks and how it can stage the knowledge and help you actually discover knowledge, understand risks, and then take actions, right? So a typical real world flow of how products are made and shipped ultimately to the customer may look something like this, right? So for example, here is a product that is being made produced by this plant, and as I'm traversing this graph, you can see that as I go to every node and edge, you can see the properties of those node and edges, and you can put as many properties on that node and edge as you want. You can have gigabytes of properties on each node if you want to, right? So there is no constraint here. And then that plant, once it produces that product, it routes it, another edge to a port, but that's not the port that ships it finally to the customer. It routes it to another port, and that port finally syncs it into the customer. In a sense, it hands it over to the customer. That's the final fulfillment. So I think the thing to notice here is that there's a physical reality in the real world, and that is getting modeled by this modeled reality in the digital twin. And there are probably a lot of more gotchas here which we are not modeling, but that's okay. You always model at a certain level of approximation. You don't try to model every nitty-gritty, right? For example, inside the port, probably it's getting handed over from one side of the port to the other side of the port, or it's getting staged in a staging area for 5 hours. But we choose not to show that detail, right? Another way of looking at this data is in a product-centric view, right? You can look at what are the bottlenecks that a product can face, can suffer in its desire to reach customers. And I want to show you this dreaded diamond-shaped supply chain, which is like something you want to avoid, right? So here, this product on the right wants to reach the customers for the orange blobs. But as you can see, from product side, it looks like it's made in 2 plants. It shipped through 2 ports. Good, there's redundancy, 50% redundancy. If one plant goes down, I have another way. But actually, if you look at the other end, they all go to the same port, and that is the only port from which the product is getting shipped to customers. You have a diamond shape, you have a problem. So if that port gets knocked out, that end port, this product can never see the light of day. This is a problem, and this is a classic resiliency problem, right? So the issue here is that you can see this with your eyes right now. It's very easy to say, there is a problem, let's fix it. But the problem is once in a real supply chain, there are millions or even billions of nodes, and you're not going to be able to, with your eye, figure out things like that. You need an AI algorithm to go and look into the network and figure out these hotspots, right? So this is very much a task of AI. This is not something you would do with human eyes typically. And finally, I just want to, for the sake of completion, call out that you can also take a customer-centric view, which port ships to this customer and what other ports feed into it and things like that. Finally, it's not just about like seeing beautiful pictures with graph, right? Actually, by querying the graph, you can get very numerical features and numerical answers. You can get statistics, you can understand connectivity and flows, sensitivity to various kinds of disruptions. Like you can literally remove edges and nodes from the graph and ask the question again. Now tell me what the KPI looks like, right? And things like that. And then, that those KPIs and those answers and numerical answers can actually be used in scorecards. And then most importantly, they can also be used as ML features, right? Input to ML models. And then they can be deep models, they can be time-based models and so on. So just a quick kind of set of things to give you a flavor of what kind of answers that GD Twin can give you. You can get histograms of some kind of scalar quantity. Here there's a product histogram in terms of some product property. You can look at whole graph statistics about what kind of locations are plants versus ports. You can calculate the carbon footprint of all the production plants based on all the things they're making. You can look at what are the most busy ports doing the most amount of shipments. You can, for every plant or production plant, you can actually calculate the product neighborhood. So this is a concept of graph, right? Graph neighborhood, where you say, what are the different things it's connected to? And you can ask the question, what are the different products that plant is making, hence it is connected to? And those things, those lists, those numbers that you're seeing here, they can all be thought of as features that go into machine learning for various kinds of objectives. So with this framework in mind, I want to now hand it over to Mayank to talk through some really great examples of how AI can be used on top of the GD Twin. Go for it, Mayank.
Thank you, Anand, for the great introduction. Just before I speak, I wanted to confirm if my voice is audible. All right. So Anand give a great introduction into how supply chains are a very chaotic systems that digital twins can be used to tame. We talked a lot about how analytics can be powered by these graphical views. What I'll focus on more is, once you have the graph and the twin setup, how does that factor into AI models built on top of it to help build resilience in your supply chain? So a specific scenario that we want to look at here is making a product to order or making a product to stock. In this case, making to order means, do I make a product when a customer order comes in and ship it out, or do I make it and stock it in my warehouses and ship it when the order comes in? So the difference between these two would be trade-offs in terms of, if you build it when the order comes in, then you need to achieve a certain SLA. You will probably be shipping it via air. You will have a net positive carbon footprint, versus when you build it to stock, you are incurring inventory and storage costs. So it becomes an optimization problem where you can take the help of AI to have an AI assisted recommendation for how the policy that you should be using. So if we go to the next slide, here we're looking at a sample data set where we have a mix of 60 different products, each having a demand and volatility variation. So the first graph you'll see that some products are inherently very volatile in their demand. So some sell a lot of units a day, some sell very few units a day. There's very spiky behavior. And the second chart here shows the lead time. So think of this as the time it takes for you to build single instance of a particular product when an order comes in. So there is a lead time going from 2 days to 14 days in order for you to assemble the product. Diving deeper into the data, you'll see there are certain types of products which, so like on the left, for example, you have an instance of a product which has relatively stable demand. You see some spiky behavior, but the total amount that you see, the difference between the minimum and the maximum isn't that high. Versus on the right, there is a second product here where there are spiky patterns in here. And this is the type of product that you need to build resilience for. If the demand really doubles in a single day, how do you meet that demand? So this is where AI comes in, right? So we have a framework that we can use to optimize the policy for make to order versus make to stock. And the first principle of building these policies is configuring your KPIs. So if you go to the next slide, KPIs are usually separate. For every company would have separate processes that they'd want to optimize. There's a couple of KPIs that we look at here: fill rate and inventory turns. Fill rate is meeting your customer SLAs. How many of the orders do you fulfill within a certain time period? And inventory turns is the rate at which your inventory moves out of your warehouses, so that you're not stockpiling inventories. This is meant to be a configurable thing though. So if you go to the next slide, you could add, for example, day sales of inventory, or you could add sustainability metrics in order to build that into the optimization itself. Now, the next lever that you get to play with in building these policies is the relative importance that you give to each of these KPIs. So in this particular case, we're using fill rate KPIs and inventory turns KPIs, and we're giving a relative importance of 0.7 to inventory turns versus fill rate. You'll see that there's two customer segments below, segment A and segment B. Segment A can be thought of as let's say a B2B segment of customers, and segment B can be thought of as a B2C segment of customers, and each segment could have their own SLAs. With this input and with these levers that you can play around with, you can generate a policy. Go to the next slide. You try to generate a policy, and then the recommendations show, hey, that for standard input, when your business is going as usual, the make to stock and make to order split is roughly 50-50. 31 products you make to order, 31 products you make to stock, and 29 products you make to order. And total units on hand are about 1,000 units. One thing that I'd like you to notice is the fitness value of around 97, comparing with where it started with, around 85-ish. This is where AI really comes in, right? So we started with an 85 a number by using baseline ABC XYZ analysis, which looks at the inventory and demand volatilities, and simulated annealing and AI algorithms put on top of that helps us improve the fitness value from mid 80s to around 97. Now, what if you want to see what would happen if I pay more, more weight to the fill rate? I want to make sure that I meet my customer SLAs. In this case, we pull the slider back from 0.7 to 0.55. And then try to see what the recommendation is. So you generate a policy, and you'll realize that, hey, in case I want to make sure that I fulfill my customer SLAs in time, the make to stock and make to order split remains relatively the same, but the total units on hand go down. Now, from 1,000 unit, there's about a 10-15% reduction, and they go down to 880. Important to note still is that the fitness value is in the high 90s compared to a baseline approach. Now comes the part where you want to build in resiliency in your supply chain. Let's say you want to model how you should build your policies when demand suddenly increases. So in this case, in this example, the segment SLA for segment A, which was previously 14, we decrease it to 5. So this is a proxy for us to increase demand. With this, we can model, hey, if my demand suddenly increases, what should be the make to stock and make to order split? And how should I be setting up my factories in order to meet that demand? So in this case, now you'll see that the split completely changes. So we are recommending that almost 90% of your products you should be making to stock, have enough safety stock on hand. So around 1,422 units on hand. This is about a 40% increase from where we started with, around 1,000 units on hand. Important to note is, despite this, the fitness value of in such constrained scenarios of the AI compared to the baseline approach is still giving you about a 10-point increase in terms of the baseline approach. Now, just wanted to summarize what we saw in the previous few slides in a set of dashboards that you can build to compare and contrast what these different policy recommendations are. So we start with, as I mentioned, ABC XYZ, which is a standard approach that you would take from an analytical point of view, looking at demand and volatility of any product. We have a make to order, make to stock split, but here is where you add the AI algorithm on top of it. So when you have a 14-day SLA, if you go to the next slide, you see the top left chart where we show the goodness of it. This is the advantage that AI gives you. It is improving the goodness of it by a significant margin, and you can play around with different KPIs to see how they are impacted. And then the third slide talks about, hey, if I want to build resilience, in reality, supply chains are complicated, as this talk has been mentioning. You shouldn't be modeling for ideal scenarios. You should be modeling for a scenario in which, there are disruptions. So let's say I want to plan for increasing of demand. So with a 5-day SLA, you can see that the AI algorithm still improves upon the baseline approach. It gives you a prediction for what make to order, make to stock split should be, and the effect on the KPIs that you're going to have. That's all from my side. I'll hand over to Anand to conclude the talk.
Thank you. Thanks, Mayank. That was awesome. And so I just want to say two more things, and maybe if you can take a couple of questions. First is that, digital twins allow you to do this analysis, right? To actually see this, to do this in computer memory and not have to change things in the real world before you figure out that it's right or wrong. So that's obviously a great benefit. And the second conclusion obviously is that, sometimes to build resilience, you have to do some sacrifices, right? You have to give up a little bit on some of your KPIs, but not a whole lot. That's the learning here, right? That back off a little bit from trying to just drive one KPI all the way. And if you do that in a nicely measured way, then you can actually make your system very, very robust. And this was a lesson that this last 2 years, 3 years of pandemic has taught for supply chains, that everything was just in time, everything was optimized for efficiency and saving cost as much as possible. And the supply chains became very fragile. They were just not set up correctly. And now that realization is definitely being absorbed, that, hey, you need to build in resiliency, and that involves giving a little bit on KPIs. That's okay. But still, you're doing much better than a non-AI and non-optimized set of configurations, right? So you can always improve, but you can also build in resiliency at the same time. And digital twins and AI are, in our opinion, the tool of the future. That is what is gonna enable the industry to actually take this as a working paradigm going forward. So we'll stop here. Thanks for patiently listening.